A wall of water taller than many skyscrapers ripped through a remote Alaskan fjord and carved fresh scars into mountainsides that had stood unchanged for centuries. Trees vanished from steep slopes hundreds of feet above sea level. Rock, ice, mud, and seawater collided with such force that seismic instruments detected the event across vast distances. One question now hangs heavily over coastal regions, shaped by glaciers and narrow inlets. How many more unstable mountains are waiting above cold northern waters? Another question follows close behind. How close did Alaska come to a maritime catastrophe involving thousands of tourists and crew members moving through one of the state's busiest scenic waterways? The disaster unfolded inside Tracy Arm, a long and narrow fjord in southeastern Alaska, a landscape known for sheer granite walls, tidewater glaciers, floating ice, and heavy summer vessel traffic. The region lies roughly 45 miles, or about 72 kilometers, south of Juneau. During peak travel months, cruise ships, charter boats, and sightseeing vessels routinely pass through the fjord to approach glaciers at the head of the inlet. Yet during the early morning hours of August 10, 2025, the fjord became the site of one of the most powerful localized tsunami events ever documented. Researchers later confirmed that the wave generated inside Tracy Arm reached approximately 1,580 feet, or around 481 meters, above sea level at its highest run-up point, making it the second highest tsunami ever measured anywhere on Earth. Only the famous 1958 Lituya Bay megatsunami in Alaska, which reached around 1,720 feet, or roughly 524 meters, exceeded it. Unlike most tsunamis, which are generated by undersea earthquakes that push enormous volumes of ocean water outward across entire basins, the Tracy Arm disaster emerged from a massive landslide crashing directly into confined water. The difference mattered enormously. Earthquake-generated tsunamis often travel thousands of miles across open oceans while gradually dispersing energy. Landslide tsunamis inside narrow fjords behave differently. The energy has little room to spread sideways. Instead, the water is forced violently upward and outward within a confined corridor bordered by steep mountains. In Tracy Arm, geography amplified destruction. The chain of events began high above the fjord near the South Sawyer Glacier. For years, glaciers throughout southeastern Alaska have been retreating, exposing unstable rock faces that were once supported by ice. As glacier ice thins and withdraws, mountainsides that depended on that frozen support can weaken dramatically. Tracy Arm sits within one of the most heavily glaciated coastal regions in North America, and the fjord's terrain reflects relentless geological pressure from ice movement, freeze-thaw cycles, and erosion. During the early morning collapse, approximately 64 million cubic meters of rock and debris, equal to more than 83 million cubic yards, detached from the mountainside and plunged into the fjord in roughly 1 minute. The volume was so immense that comparisons quickly emerged to major human-made structures. Some researchers noted that the amount of collapsed material could fill the Great Pyramid of Giza more than 20 times. The falling rock mass accelerated rapidly down steep terrain before slamming into deep water. The impact displaced colossal quantities of seawater instantly. In confined fjords, displaced water cannot spread smoothly across wide coastlines. Instead, it rebounds vertically with extraordinary violence. Tracy Arm itself measures roughly 30 miles, or nearly 48 kilometers, in length and less than 1 mile, or approximately 1.3 kilometers, in width through some sections. The fjord walls rise dramatically from the water, creating a natural channel that intensified the upward surge. Evidence of the tsunami remained visible long after the water retreated. Satellite imagery and aerial surveys revealed stripped vegetation lines reaching astonishing elevations along the fjord walls. Entire sections of forest disappeared from slopes hundreds of meters above normal sea level. The wave blasted rock, soil, and trees from steep mountainsides, leaving exposed scars across large sections of the inlet. Scientists reconstructed the event using satellite imagery, seismic records, field mapping, drone observations, and mathematical modeling. No direct video footage of the initial wave exists, partly because the landslide occurred at around 5:26 in the morning local time, long before the daily arrival of most tourist vessels. That timing likely prevented fatalities. The absence of casualties remains one of the most remarkable aspects of the disaster. Tracy Arm is not an isolated wilderness visited only occasionally. During summer months, more than 20 tourist vessels per day may enter Tracy Arm and neighboring fjords. Large cruise ships carrying several thousand passengers regularly navigate the area. Had the landslide occurred later in the morning or during peak sightseeing hours, ships could have faced catastrophic conditions inside a narrow waterway with little room for maneuvering. The megatsunami did not simply produce a single towering wall of water and disappear. Researchers documented prolonged oscillations inside the fjord after the initial impact. Water continued sloshing back and forth in what scientists call a seich, a standing wave pattern that can persist for extended periods inside enclosed or partially enclosed basins. In Tracy Arm, these oscillations lasted for many hours and generated continuing dangerous currents and surges. Seismic instruments recorded the landslide as an event roughly equivalent to a magnitude 5.4 earthquake. Signals generated by the collapse propagated far beyond Alaska. The event demonstrated how large landslides can produce seismic signatures strong enough to be detected globally, even without major tectonic fault movement. The disaster also underscored the difference between traditional tsunamis and megatsunamis. The term megatsunami generally refers to extremely large waves generated by massive localized displacement events, such as landslides, volcanic collapses, or asteroid impacts. Unlike conventional tsunami waves crossing open oceans at lower heights, but enormous wavelengths, megatsunamis can reach staggering vertical elevations near the source while affecting more geographically limited regions. Alaska has long been associated with some of the world's largest tsunami events because of its combination of steep coastal topography, seismic activity, glaciers, and unstable mountain terrain. The 1958 Lituya Bay disaster remains the most famous example. That event occurred after a major earthquake triggered a giant rock slide into a narrow bay, producing a wave that stripped vegetation from slopes more than 1,700 feet, or about 524 meters above sea level. The Tracy Arm event now ranks directly behind it in recorded height. Yet Tracy Arm differed from Lituya Bay in important ways. Lituya Bay occurred in an era before modern satellite monitoring, advanced remote sensing, and high-resolution geophysical modeling. Tracy Arm unfolded in a technologically connected age. Researchers were able to reconstruct slope movement patterns, analyze satellite imagery before and after the collapse, and map changes to the fjord landscape with unprecedented detail. Satellite analysis revealed the extent of terrain failure around the South Sawyer Glacier area. Before the collapse, sections of the mountainside already showed signs of instability. Over time, retreating glacier ice had removed support from lower slope sections. Water infiltration, freeze-thaw expansion, and erosion likely contributed additional stress. The combination created conditions favorable for catastrophic failure. The event added to growing global concern about landslides in glaciated fjords. Similar disasters have occurred in Greenland, Norway, and parts of Western Canada. In many of these regions, glaciers are retreating rapidly, exposing slopes that remained buttressed by ice for centuries or millennia. Once that support disappears, the stability of surrounding mountains can deteriorate. Tracy Arm's geography amplified danger at nearly every stage. The fjord's steep walls acted almost like funnels, forcing displaced water upward. Deep water near the landslide zone allowed enormous volumes of rock to penetrate directly into the fjord without significant slowing. Narrow dimensions prevented energy from dispersing outward efficiently. Instead, the water surged vertically against surrounding slopes. Researchers found evidence that the wave reached elevations surpassing famous global landmarks. At roughly 481 meters, or 1,580 feet, the run-up height exceeded the height of the Empire State Building and rose well above the Eiffel Tower. These comparisons illustrate the extraordinary scale involved, though the wave's immense height occurred mainly near the source area, rather than as a uniformly moving ocean wall. The aftermath transformed portions of the fjord landscape permanently. Vegetation removal exposed fresh rock surfaces visible from space. Debris fans altered shorelines. Water turbulence redistributed sediment and damaged ecosystems along steep coastal margins. NASA imagery later documented clear before and after changes across large sections of Tracy Arm. Although no large ships were directly struck inside the most dangerous zone, witnesses farther away reported unusual wave behavior and violent water movement. Boats anchored miles from the collapse experienced strong surges and rolling motion as water rapidly rushed through the fjord system. These observations highlighted how destructive energy propagated beyond the immediate landslide site. The timing of the event became a central focus after reconstruction efforts clarified the scale of destruction. Cruise tourism in Alaska has expanded significantly over the past decade, with millions of passengers visiting coastal fjords annually. Tracy Arm and neighboring glacial inlets remain among the most sought-after scenic destinations for cruise itineraries because of towering cliffs, wildlife, waterfalls, and floating glacial ice. Summer vessel schedules often concentrate traffic during daylight hours when visibility is highest and glacier viewing conditions improve. The landslide occurred before the typical daily arrival window for large tourist vessels. Had it taken place later in the morning, evacuation inside the narrow fjord would have been extraordinarily difficult. The disaster also exposed limitations in hazard monitoring across remote coastal environments. Many glaciated fjords contain unstable slopes that are not continuously monitored. Detecting exactly when a mountainside may collapse remains extremely challenging. Even identifying which slopes pose the highest danger requires extensive geological assessment. Scientists later identified signs of seismic activity and movement in the days preceding the collapse. However, translating such signals into real-time public warnings remains difficult. Remote fjords often lack permanent instrumentation networks dense enough to provide reliable early alerts for sudden slope failures. The Tracy Arm megatsunami therefore became not only a geological milestone but also a warning about coastal hazards in rapidly changing Arctic and subarctic environments. Alaska's coastline contains countless fjords carved by glaciers over thousands of years. Many are lined with steep, fractured mountains vulnerable to collapse under the right conditions. Climate shifts have intensified scrutiny of these regions because warming temperatures affect both glaciers and permafrost stability. As ice retreats and frozen ground thaws, slopes once stabilized by long-term freezing can weaken. Water infiltration into fractures may further destabilize rock masses. In mountainous coastal terrain, even a single catastrophic slope failure can generate devastating local tsunamis within seconds. The Tracy Arm event joined a growing list of climate-linked geological disasters observed across polar and alpine regions. While earthquakes remain major tsunami generators worldwide, landslide tsunamis in narrow fjords may become increasingly important hazards in glaciated environments undergoing rapid transformation. Historical records show Alaska has repeatedly experienced destructive waves generated by landslides. Beyond Lituya Bay, other fjords and inlets have witnessed large localized tsunami events over the past century. Yet Tracy Arm's measured height places it among the most extreme ever documented scientifically. The wave's destructive reach extended high above normal marine influence zones. Forests growing hundreds of meters above sea level were uprooted or shredded. Soil layers disappeared from steep slopes. Fresh scars remained visible months later. Such landscape transformation provides physical evidence of the enormous kinetic energy transferred during the event. Researchers studying the aftermath emphasized how the tsunami interacted dynamically with terrain. Water rebounding off steep cliffs generated secondary surges and reflected waves within the fjord. Energy ricocheted through the confined basin rather than dissipating immediately into open ocean. Because Tracy Arm opens into larger waterways connected to Alaska's Inside Passage, the event also raised broader navigational concerns. Even localized megatsunamis can create hazardous currents, surges, and debris fields, extending well beyond the immediate impact zone. Floating timber, rock fragments, and sediment plumes may endanger vessels far from the original collapse site. The landslide itself altered parts of the fjord shoreline dramatically. Massive quantities of rock entered the water, reshaping coastal contours and underwater topography. Such changes can influence navigation routes, sediment movement, and marine habitats long after the initial event. One striking aspect of the disaster involved the duration of detectable seismic and hydrodynamic effects. Researchers documented oscillations lasting more than a full day in some analyses. This prolonged motion reflected the extraordinary volume of displaced water trapped inside the fjord system. Satellite technology played a major role in reconstructing the sequence of events. Modern Earth observation platforms captured detailed imagery of vegetation loss, debris distribution, and altered shorelines. Combined with seismic records and field mapping, scientists assembled one of the most comprehensive reconstructions ever produced for a megatsunami. The Tracy Arm event also demonstrated the importance of remote sensing in regions where direct observation is sparse. Much of Alaska's rugged coastline remains difficult to access quickly after disasters. Satellite analysis therefore becomes essential for understanding hazard impacts and identifying ongoing instability. In the months following the megatsunami, discussions intensified regarding hazard assessments for cruise routes and tourist destinations across Alaska's fjords. Operators routinely market glacier viewing experiences that bring vessels close to steep coastal terrain. The Tracy Arm collapse revealed how quickly apparently scenic environments can transform into zones of extreme danger. The event's location near glacier fronts added another layer of concern. Tidewater glaciers attract vessels because of dramatic calving activity, floating icebergs, and wildlife viewing opportunities. Yet glacier retreat can simultaneously destabilize adjacent slopes, increasing landslide risk precisely where tourism concentrates. Despite the terrifying scale of the tsunami, the disaster received relatively limited immediate global attention, partly because no fatalities occurred and the location was remote. Only later, after scientific studies confirmed the wave's historic height, did the event gain broader recognition. The contrast between physical destruction and human impact remains remarkable. A wave capable of stripping mountainsides bare produced no direct loss of life, largely because of timing and geography. Few disasters demonstrate more clearly how coincidence can separate a historic geological event from a mass casualty catastrophe. Alaska's coastal fjords continue attracting tourists precisely because of their dramatic landscapes. Towering cliffs, glaciers, waterfalls, and narrow waterways create some of the most visually striking marine environments in North America. Yet those same characteristics also create conditions favorable for megatsunami formation when large slope failures occur. Tracy Arm now stands as both a geological landmark and a warning embedded directly into the landscape. Fresh scars on the fjord walls mark the path of the wave. Stripped vegetation lines reveal the astonishing height reached by displaced water. Satellite imagery preserves evidence of transformation visible even from orbit. The event also broadened understanding of how rapidly large coastal landslides can unfold. Tens of millions of cubic meters of rock collapsed within roughly 1 minute. In confined fjords, that timescale leaves virtually no opportunity for evacuation once failure begins. Nearby vessels would have little chance to escape a rapidly rising wall of water inside a narrow inlet. Researchers examining the disaster emphasize that megatsunamis differ fundamentally from ordinary storm waves or even many earthquake tsunamis. The energy released near the source can be extraordinarily concentrated. In Tracy Arm, water surged upward against cliffs with immense force rather than spreading broadly across coastlines. The megatsunami also reinforced Alaska's reputation as one of Earth's most geologically dynamic regions. Earthquakes, volcanic eruptions, glacial movement, landslides, and coastal erosion constantly reshape the state's vast landscape. Tracy Arm demonstrated how those forces can combine suddenly and violently. As scientific analysis continues, the disaster is likely to influence hazard mapping and monitoring programs in glaciated fjords worldwide. Coastal regions in Greenland, Norway, Canada, and parts of Patagonia contain terrain with similar characteristics: steep slopes, retreating glaciers, confined waterways, and increasing tourism activity. The towering wave inside Tracy Arm will ultimately be remembered not only for its historic height, but also for the narrow margin separating survival from catastrophe. One of the largest tsunamis ever measured erupted inside a popular tourist fjord, yet the timing spared thousands of potential visitors from direct exposure. The mountainside collapse lasted about 1 minute. The wave transformed the fjord within moments. The scars left behind may remain visible for generations.